We showed in Chapter 18 that when a charge is placed in an electric field, it experiences a force given by F equals QE. This force points in the same direction as the electric field for positive charges, and opposite the direction of the electric field for negative ones. It turns out that charges will also feel forces in magnetic fields, a magnetic force, provided two conditions are satisfied. First, the charge must be moving. In other words, there is no magnetic force on a stationary charge. Second, there must be a component of the charge's velocity that is perpendicular to the direction of the magnetic field. To examine the second condition, consider the figure below, which shows a positive test charge plus Q0, moving with a velocity v through a magnetic field B. The field is produced by magnets, not shown in the drawing, and is assumed to be constant in both magnitude and direction. If the charge moves parallel or antiparallel to the field, as in the figure, the charge experiences no magnetic force. If, however, the charge moves perpendicular to the field, as shown in the next panel of the figure, the charge experiences the maximum possible force, F max. In general, if a charge moves at an angle theta with respect to the field, as shown in the last panel of the figure, then only the velocity component v sine theta, which is the perpendicular component to the field, contributes to the magnetic force. This force F is smaller than the maximum possible force. The component of the velocity that is parallel to the magnetic field yields no force. The figure shows that the direction of the magnetic force is perpendicular both to the direction of the magnetic field B and the charge's velocity v. Over the next two chapters we will use a series of right-hand rules, which will help us in determining the directions of forces and magnetic fields for different situations. Here we introduce right-hand rule number 1, which is used to determine the direction of the magnetic force acting on a charged particle moving in a magnetic field. Extend the right hand so the fingers point along the direction of the magnetic field B, and your thumb points along the velocity v of the charge. The palm of your hand then faces in the direction of the magnetic force F that acts on a positive charge. It is as if the open palm of the right hand pushes on the positive charge in the direction of the magnetic force. If the moving charge is negative instead of positive, however, then the direction of the magnetic force is opposite to that predicted by right-hand rule 1. Thus, there is an easy method for finding the force on a moving negative charge. First, assume that the charge is positive and use right-hand rule 1 to find the direction of the force. Then reverse this direction to find the direction of the force that would be acting on a negative charge. Now that we know how to determine the direction of the magnetic force on a moving charge, how do we calculate the magnitude of the force? In doing this, we will end up defining the magnetic field in much the same way we did for the electric field case. Recall that the electric field at any point in space is the electrostatic force per unit charge that acts on a test charge Q0 placed at that point. In other words, to determine the electric field E, we divide the electrostatic force F by the charge Q0. In the magnetic case, however, the test charge is moving, and the force depends not only on the charge Q0 but also on the velocity component v sine theta that is perpendicular to the magnetic field. Therefore, to determine the magnitude of the magnetic field, we divide the magnitude of the magnetic force by the magnitude of the charge and also by v sine theta, according to the following definition. The magnitude B of the magnetic field at any point in space is defined as B equals F over Q0 v sine theta, where F is the magnitude of the magnetic force on the test charge, Q0 is the magnitude of the test charge, and V is the magnitude of the charge's velocity, which makes an angle between 0 and 180 degrees with the direction of the magnetic field. The magnetic field B is a vector, and its direction can be determined by using a small compass needle. The SI unit of magnetic field is the Newton second per coulomb meter, which is also known as a Tesla. The unit is called the Tesla, a tribute to the Croatian-born American engineer Nikolai Tesla. Thus, 1 Tesla is the strength of the magnetic field in which a unit test charge, traveling perpendicular to the magnetic field at a speed of 1 meter per second, experiences a force of 1 Newton. Because a coulomb per second is an ampere, the Tesla is often written as 1 Newton per ampere meter. In many situations, the magnetic field has a value that is considerably less than 1 Tesla. For example, the strength of the magnetic field near the Earth's surface is approximately 10 to the minus 4 Tesla. In such circumstances, a magnetic field unit called the Gauss is sometimes used. Although not an SI unit, the Gauss is a convenient size for many applications involving magnetic fields. The relation between the Gauss and the Tesla is 1 Gauss is equal to 1 times 10 to the minus 4 Tesla.